All right, so welcome, my Math 70s. Today I'm going to be going over the Exam 3 review. Don't know why that conference Zoom part is stuck there or whatever. And you can find this on WebAssign. I would highly suggest starting Exam 3 review before you start Exam 3. Just to make sure that you're comfortable with the problems and the methods that we're using. I am going to have you show your work for all the problems in Exam 3. So you do need to understand some of these details that we'll be covering tonight. So I'm just going to go ahead and start with number 1. I'll try to do some of them on here. If there's not enough space, I will move to the whiteboard, which is probably the best option. Okay, so for the first one, we want to determine whether the sequence converges or diverges. So first thing to note is that it's a sequence we're talking about. So we just want to find the limit of this essentially. As n goes to infinity, so the limit of a sub n. And that's going to be the limit of n squared. I'm going to go ahead and make this into a fraction, n squared divided by e to the 3n. What that leads me to is when I split up this limit, I actually get an infinity over infinity type of limit. So that tells me I'm going to need to use L'Hopital's here. So essentially, remember for L'Hopital's, you would be going into x terms first so that it's a real valued variable instead of n, which is a whole number value. So let's look at the limit as x goes to infinity of x squared over e to the 3x. If you forget this part and you still do the limit in terms of n, I'm not going to mark you down for it. Just technicalities. So whenever you use L'Hopital's, definitely put an LH here of some sort to let me know that you are taking the derivative of top and bottom. So we have limit x goes to infinity, 2x divided by 3e to the 3x. That's still going to give an infinity over infinity for the limit, so we're going to need to take L'Hopital's again. That's going to be limit as x goes to infinity of 2 over 9 e to the 3x. So from here, the bottom as x goes to infinity, e to the 3x, oops, sorry, that's fine, e to the 3x moves toward infinity. So remember, if this bottom portion here moves toward infinity, that means your entire limit moves to 0. Okay. So that's the gist of what you would need to show for this particular problem. The limit is 0. Let's go ahead and work out number 2, which is also from 11.1. That's another one where you're finding whether or not the sequence converges or diverges. So you just want to figure out if there's a limit that your a sub n converges to as n goes toward infinity. So for this one, I'm going to use a less formal. This is the one where we're just going to keep it in terms of n. So you have the limit as n goes to infinity. You have an ln rule that you can use here, log rules. This is ln of n plus 3 divided by n. And then that's the limit as n goes to infinity of ln. You can actually divide the top and bottom inside the ln by the max term here of n. So let me put that over here. Divide the top by, can't see that. I'll just do it in the next step. So that's the limit as n goes to infinity of ln of 1 plus 3 divided by n over 1. Now for this, all I would need you to show is that, basically since ln x is a continuous function, we could move the limit inside of the argument of ln. So we can evaluate what the limit as n goes to infinity of 3 over n will be, and that would just be 0. So once you've looked at the limit of the stuff inside, we find out that that's ln of 1, and ln of 1 is 0. So we also have 0 for our limit for number 2. And then just more formally, the way that that's working, you have ln, and then that limit comes inside, limit as n goes to infinity of 1 plus limit as n goes to infinity of 3 over n divided by a limit n goes to infinity of 1. You would not need to show all this detail. This is enough. We would still find out that this goes to 0, this goes to 1, this goes to 1, and we'd come to the same conclusion. Go ahead and save a picture of that if you're going to need any of it immediately. I'm going to clear this out and then move to the next problem. I should have this up by tomorrow morning at the latest. I'm hoping that the video is going to be done later tonight. Let me clear all this out, and then let's move down. So this one I had already put in just to double check it before. Consider the following geometric series, find the common ratio, whether or not you have a convergent or divergent series, and then if it is convergent, find its sum. So for this part, recall for a geometric series, we're going to have your series S be equal to summation n equals 1 to infinity of a times r to the n minus 1. A is some constant, and r is your ratio. So if S is indeed convergent, you need the absolute value of r to be less than 1. And then your sum, S, will be represented by a over 1 minus r. Okay, so for this, S here is equal to the geometric series you have here. It's not in summation form, so you have to manipulate it. So S is, we have 2 plus, change these guys into fractions. You have 4/10, 8 100ths, 16 1,000ths, and so on and so forth. Keep manipulating. You're trying to have some constant, the same constant multiplied to every term. and then have the same R value for each term. So we have 2 plus, I'm going to factor a 2 out of all of these. So 2 times 2 over 10 plus 2 times 4 over 100 plus 2 times 8 over 1,000, and so on and so forth. That's 2 plus. Now, start trying to find a pattern. Since you've already pulled out a constant, we kind of have an inkling that A is going to be 2. But then what do we do with this ratio part here? Okay, well, we have 2 times 2 over 10 plus 2. This is 2 over 10, the quantity squared. Let's go ahead and put a first power on this one too. Plus 2 times 2 over 10 cubed, and so on and so forth. Of course, my cat would be using the box right now in the living room. Hopefully you can't hear that. So here, your n values, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and so on and so forth for your summation. So S, what we find is the summation n equals 1 to infinity. We have 2 multiplied out front. 2/10 simplifies to 1/5. And then notice the pattern. There's technically a 2 over 10 to the 0 power here. First power, second power. What do the powers relate to the n's? That's n minus 1. Okay. So this is our geometric series. What we find from here is that A is equal to 2 and R is equal to 1/5. Now, the absolute value of R is still equal to 1/5, and that is less than 1, which will be important later. So here's your absolute value of R. Okay, 1 second. Let me pause this. All right, continuing on here. So R, the absolute value of it is going to be 1/5. Because 1/5 is less than 1, we will have a convergent geometric series. Can you please stop it? Okay, 1 second. Thank you. Oh my goodness. Okay, and now if we have a convergent geometric series, we should be able to use this as our sum equation. So the sum should be equal to A divided by 1 minus R. Don't use the absolute value of R here. You want to use R. So if R actually came out to negative 1/5, which it could occur sometimes, then you'd want to put a negative in here. That's 2 divided by 4/5, which is 2 over 1 times 5 over 4, which gives you 10/4, which is 5/2. So that completes number 3. Take a picture if you think you'll need it. Before we get too much further into 11.2, let me go ahead and just take a quick pause from recording. All right, so I'm going to go ahead and clear all this out, and then we're going to move to problem 4. Determine whether the series is convergent or divergent. This is still an 11.2 problem. You're eventually going to want to get used to finding your series convergence or divergence without knowing which section it's from. Practice with 11.7 will help with that. So now we want to know if the series is convergent or divergent. So for that, you're going to need a different set of rules. It doesn't follow the same set of rules as the sequences. So remember for this, you have a formula sheet that you're allowed for exam 2. Sorry, exam 3. It's available on Canvas under files and extras, I believe. All right. So essentially for this part, your first go-to in terms of tests should be the nth divergence, or the nth term divergence test. Which you can just simplify by calling it the divergence test. You will need to reference which tests you use in detail when you give your problems in. Okay, so essentially, the first thing we're going to do is check the limit of our a sub n value, and our a sub n is going to be the part inside the series. Okay, here's a hint for this. If you have the same leading term that has the max power in numerator and denominator, the limit's probably not 0. So that's the best way to check. All right, so limit as n goes to infinity of a sub n. The limit as n goes to infinity of k squared. Yep, hold up, let me change that right quick. Do note that we have k's, not n's here, so let me change that guy. So use the index value here. So a sub k. So we want the limit as k goes to infinity of a sub k. That's the limit as k goes to infinity of this guy right here. What we're going to do is divide by k squared everywhere, top and bottom, since that's the max degree that we have for top and bottom. Oops. Okay, so now we have the limit as k goes to infinity. On the top, we have a 1. On the bottom, 1 minus 2 over k plus 3 over k squared. And again, you could formally show that the limit goes inside for each one of these terms, but you don't have to do that. Just think, okay, for this term here, as k goes toward infinity, what happens to 2 over k? Well, that goes to 0. Same thing for 3 over k squared. And then the limit would be 1 for the top, limit would be 1 for the bottom. So you're essentially going to get 1 for your limit. Okay. So what we found here, essentially for the nth term divergence test, what that states is if the limit as k goes to infinity of a sub k is not equal to 0, then your series S is not convergent, aka divergent. So this is your S here. Okay, so your conclusion that you're going to want to write in your show work portion, you wouldn't have to write it here. For this part, you'd actually want to write diverges in. Remember, you're not talking about the sequence being convergent. The sequence is convergent to 1, but the series is not convergent because the sequence does not converge to 0. So conclusion, because limit as k goes to infinity of a sub k is not equal to 0, the series, you could just abbreviate it S if you do this. Like if you call S this series up here, you don't have to repeat it, but I'll just do it for good measure here. The series S, which equals the summation k from 1 to infinity of a sub k, is divergent. So do note the difference between a sequence being convergent and a series being convergent. Go ahead and take a picture if you're going to need it. I'm going to move to number 5 next. Clear this out. So number 5, determine whether the series is convergent or divergent. For this part, so let's go ahead and establish that this is going to be our S. And before we start trying to figure out what A sub n is, remember that you can actually split the summation. If there's a sum between, you can split the summation. Okay, so now we actually need to evaluate 2 different series. This is the first series. Call it series A. And then the second series, series B here. So I'm just going to start with A, even though if you've already done your research into the P series stuff, you would know that the second series is indeed divergent, which would make the entire series divergent. But let's just start with series A. Okay, so you have here what looks like a geometric series, but it doesn't quite have the form you need yet. Remember, if n is starting at 1 here, you need to have a power of n minus 1 on your R stuff in here. So you have the 3, which is a constant, can come out front. You have your summation n equals 1 to infinity. What we're going to do, we're going to break off one of the 1/5. And then we have 1 over 5 to the n minus 1 left over. Okay. So we see that 1/5 is constant, so we can pull that outside as well. Multiply it to the 3, you get 3/5. You have summation n equals 1 to infinity. And then you have 1/5 n minus 1. So this is indeed a geometric series. Notice we have the correct form we want here. Again, you want to have n equals 1 here with an n minus 1 for your R here. So we find out that A is equal to 3/5. R is equal to 1/5. And the absolute value of R is less than 1. So this actually would be a convergent geometric series. But before you start finding a sum for it and stuff, check series B to make sure it's convergent as well. Because if it's not convergent, you can't do anything with it. If series B is convergent, you just add up the values here. All right, not that you'd want to do that. Again, you only need to state convergent or divergent for this, okay? All right, so let's go to series B here. Essentially for this one, this is a divergent harmonic series, which is a type of P series. Recall, for P series, you're going to have some kind of series n equals 1 to infinity, and you have 1 over n to the P. If P is greater than 1, you have a convergent P series. Specifically greater, not even equal to 1. Okay, and we'll find out eventually that this comes from the integral test. You could check. If you need to see more information about that, let me know. I'm actually thinking about doing a separate video about P-series just to go over the different cases that you can have for checking if your integral is convergent, and then also checking if your series is convergent. All right, so what we see here is that for our case, P is equal to 1. So that's outside of this bound here. We do have a divergent series. So since series B is divergent, but series A is convergent, you're gonna have divergent for your series S. Let's even write the conclusion in here just so it feels more concluded. Since series A is convergent, but series B is divergent, series S is also divergent. Okay. Take a picture if you need it. So like for this particular one, I wouldn't need to see a bunch of detail written out for this. Definitely keep track of the P series and the harmonic series, which is a type of P series, so that you just automatically can refer to those conclusions here without having to go through all the intermediate steps. Take a picture if you need it. I'm going to clear this out and move on to number 6. So number 6 from 11.3, determine whether the series is convergent or divergent. So for this one, don't get too creative. Like, let's even do this in red so we know we don't do it. You can't split this up and just say like, okay, well, let me bring the 4 outside. And now I have 4 times this series. I just split it like this. That would be so convenient, but we cannot do this, okay? Cannot do this. So let's clear that messiness out. Okay, so from 11.3, this is actually the integral test. I do want to cover what you're going to need to write out formally for your show work to make sure that you get this completely right for your exam. So first thing to note is that if you were trying to check the divergence test first, this limit of a sub n here is actually going to be 0, so that doesn't give you any information. So integral test is usually the second test you move on to. You have it on your formula sheet. You can use the sheet to help you out here, but essentially you're going to start with an a sub n. And then what you're going to want to do is make a sub n, which is a function of n, into a function of x. Okay, so x is a real valued variable, n is just whole numbers, 1 and greater. So for this particular problem, f of x would be equal to 4 over x squared plus 9. Okay, now you need to check the condition. I'll be sweet if you at least write your conditions in, but you haven't formally checked them. That's fine. I'll still give you credit for it, but you do need to have these conditions stated. So one condition is that f of x is positive for some interval of x, it's typically from 1 to infinity, but not all the time. So sometimes you'll need to check what the lower bound is. You also need to check that f of x is continuous for the same interval of x. And then finally, you need to check that f of x is decreasing for the same interval of x. Okay. So essentially, for this one, to check our conditions, one, f of x equals 4 over x squared plus 9. Hopefully you can see that for values of x1 or greater, this will indeed be positive. For x being 1 up to infinity. The reason for that, kind of think 4 is positive, right, all the time. So in order to have your function be positive all the time, you need the denominator to be positive as well. X squared is always positive. And if you add 9 to that, just gets more positive, okay? So check. 2. F of x, is it continuous over your particular bounds? So remember, there's only 2 ways you get a discontinuous function. One is if you have a denominator that's equal to 0 for some value of x. The other one is if you have an even root, okay? So here, we need to check the denominator. Okay, so you have x squared plus 9. When is that equal to 0? Well, never, okay? Essentially, again, positive, more positive, can't be 0. A formal way you could do this, okay, you don't want any i's to be in there. Otherwise, it's an imaginary number, not a real one. Okay, we're concerned about the real ones. Okay, so let me erase that. Okay, so what we found is that the denominator never equals 0. For the bounds that we were testing, 1 to infinity. So that gives us our second check. F indeed is continuous. And then the third bullet point here, we need to check decreasing. Whenever you're doing that, you need to check f prime of x when it's less than 0. Okay, so let's see, am I gonna have enough room on this? Let me do this. Let me save a picture of this, and then I'm going to start a new share in a whiteboard so I have more space. Okay, I don't know what's going on here. Let me stop my share first. Hopefully I didn't lose all that. So this is the number 6, D3 review. Check f of x is decreasing. So we're going to check when f prime of x is less than 0. So recall f of x is equal to 4 over x squared plus 9. So this is when you need to bring in your Calc 1 knowledge. Remember f prime here, we're going to need to use quotient rule. So rule of thumb, just take the bottom function and square it. And then put the bottom function as it is up top, and then take the derivative of the top. Subtract, take derivative of bottom, multiply by top. So this whole first portion cancels out because you have something times 0, factor times 0. The second bit is negative 8x over x squared plus 9, the quantity squared. You can, so from this point, you can just show that this is less than 0 for x between 1 and infinity. More formally, let's see, so you could just show this and that's fine. But more formally, just looking at the bottom is always positive, right? And then when x is 1 or greater, the numerator is always negative. So you have a negative over a positive, which always gives you a negative. So we did check that f of x is indeed decreasing on our bounds for x. If you need a picture take one, I'm going to, I'll actually just clear it out on this page and then just go ahead and get started here. So let me clear all this. Oh, I'm sorry, Mama. My cat is so mad at me. No attention. Okay, so now once conditions 1, 2, and 3 have been satisfied, we are ready to start the integral test. So you must state those conditions are satisfied first before you get full credit for these types of problems. So now, integral test can be used. So essentially for the integral test, we're checking the integral 1 to infinity of f of x dx, which in this case is 1 to infinity integral of 4 over x squared plus 9 dx. Okay, so what we're going to do, we're going to put our limits in here, which is necessary. First thing I'm going to do, move the 4 out because I don't like working with constants inside of my integrand if I don't have to. And then we're going to go ahead and put this limit in here. Limit as t goes to infinity, and then our bounds are going to change. We're going to have 1 up to t. Same function f of x inside here. Oops. Slightly different. Remember we took the 4 out, so just a 1 up top now. And then for this one, we actually need to use our old school knowledge from chapter 7. This is going to be a trig substitution. And what we're going to do, we're going to so remember, go back and look at your forms for trig sub. I know that I'm going to want to use x as 3 tangent theta here, because square root of 9 is 3. And then I want, when I square my x term, I want to get an identity where I have some trig function squared plus 1. Okay, which should give me a secant if I use a tangent in there. Okay, so now we have our dx. That's going to be 3 secant squared theta d theta. Don't forget your d theta. Okay, and then we can also go about changing our bounds here. Just be careful. If it's easier, you can kind of maneuver leaving off the bounds, but it gets a little tricky when you have a limit in here. So we have, remember these are x values here. When x is equal to 1, we have 1 equals 3 tangent theta. So solve back for theta, because you want theta bounds now, since your integrand is going to be in terms of theta. So 1/3 equals tangent theta, and tangent inverse of 1/3 equals theta. You could also use arctan of 1/3. So that's going to be our new lower bound. in theta. And then for the next part, for t, you have to think about as t is going toward infinity, that would be the same as what happens as x moves toward infinity. Essentially, for this part, you can think you have x, that'd be a growing number. Let's just maneuver this a little bit. Isolate your tangent theta and think about what happens as x over 3 essentially starts to go to infinity. Well, that means that tangent theta is moving toward infinity, and that happens when theta moves toward pi over 2. So trig stuff, got to go back and review trig stuff as well. So let's redo our integral over here. We have 4, and then we still, we can keep the same limit t, but t is now going to pi over 2. Lower bound is tangent inverse of 1/3. Upper bound is pi over 2. Oops, sorry, t. Since we would still get an undefined there in theta terms. Okay, so now remember here, we have to figure out what dx is, and I'm actually going to change my format right here so that I don't have to put dx on the side. Okay, so dx is 3 secant squared theta d theta. X is 3 tangent theta. That quantity is squared. And you have your plus 9 off to the side. Go ahead and save a picture of that if you're going to need it. I'm going to get rid of the trig sub stuff so that I have more room to go over the integral here. Okay, and then I'm going to select all of this. Okay, that's not going to work. Let me just erase this. Okay, that didn't work either. Okay. Select this and move it up. Okay. So now our integral here, we still have our 4 out front. I'll just put the limit in the same color now. And the bound, same color. If you really don't like the bound thing, again, just leave it off. Do everything in theta terms first, go back to x, and then put the same bounds back on. All right, so now we are going to manipulate this a bit. So keep this part in green. We have 3 secant squared theta d theta divided by 9 tangent squared theta plus 9. Factor a 9 out here. So we're going to have 3 secant squared theta d theta divided by 9 times tangent squared theta plus 1. Okay, so from the 3 over 9, we get 1/3, and we can multiply that to the 4 out in front to put the constant out front. Okay. And then now, remember that this part here is equal to secant squared theta, trig identity. So what we have on the inside here is secant squared theta d theta divided by secant squared theta. And remember, you can skip the absolute value step that we went over. It's fine to do that. I won't mark you down for it. Take a picture if you need it. I'm going to clear out the vast majority of the top here. Okay, so continuing with this, let's erase this, this. Pretty much everything but the last step. So let me put a dot, dot, dot in here so that we can remember we did some other steps here. Okay, and then we'll just move this bit up. Or not. There we go. Okay, so we have 4/3 limit as t goes to pi over 2. Tangent inverse 1/3 on the bottom, t up top, and then we get d theta inside of our integrand. Let's use one color now. 4/3 limit t goes to pi over 2. You have tangent inverse of 1/3 as your bottom bound, t is your top bound. Oh, sorry, I didn't want to do that. We can go ahead and take the integral, yeah? Integral of d theta would be theta. You still have your same bounds on the bottom here. T up top. Now, I want to emphasize, keep your limit on here until you plug your t's in. So t minus tangent inverse of 1/3. So as t goes to pi over 2, would this be a real defined value? Yeah, you could replace it with pi over 2. Okay. And then you don't actually have to evaluate what this number is, but it actually is a real number. Okay, so hopefully you can see this. What we found is that the integral, let's call this star. Star is a convergent integral. Okay, thus the series that we were testing, I gotta go back to this sucker. It's also convergent. By integral test. Okay. Take a picture if you need it. Ask questions if you need. And I otherwise will go ahead and move on to number 7. Actually, I'm going to skip number 7 for now. Number 7 is another integral test. I'll give you a hint for that one, but I'm going to skip it for the most part for right now. So let me go ahead and clear this out. And then stop share, go to, here we are. Okay. So for number 7, again, this is another integral test. That's ugly. So remember to check your f of x conditions first. One, that it's positive, continuous, and decreasing over an interval that's at least from 1 to infinity for x. And then if those all apply, you can use the integral test. Okay. For number 7, you're going to be using partial fraction decomp. Inside the integral. And then what you should get for the actual integral itself is -5 ln 2 plus 5, which is a real number. Okay, so we're actually going to have convergence for number 7 as well. So state your conclusion. Since the integral converges to, since the integral is convergent, our series is convergent. All right, so far so good. Let me save that picture. And then let me take a quick break. I need to use the restroom real quick. Let me pause recording. All right, you guys, so I just went over the details, number 7, the ones you'll need to know, but I'm going to leave that one for you to try. Number 8 and 9, I'm sure you can guess these are not going to show up on your exam because they're too easy for the most part in terms of just being able to choose a multiple choice answer. But I want you to understand what's happening with this. This is from section 11.4, which is comparison testing. There's 2 types. There's the direct comparison test, which is usually just referred to as the comparison test. And then there's also the limit comparison test, which is referred to as LCT. So I usually, if you see me do it, I refer to it as DCT and LCT. So basically, review my notes on this. I'll go through some of these details, but here's what we have for this particular problem. Suppose the series A sub n and series B sub n are series with positive terms, and series B sub n is known to be convergent. Okay, so this is very important. This is also important. If A sub n is greater than B sub n for all n, what can you say about the series of A sub n? So let me be more specific with this. If sequence A sub n is greater than sequence B sub n terms for all n, what can you say about the series A sub n and why? So for this, you have for part A, A sub n is greater than B sub n for all n. Okay, so what that's going to mean is that the series A sub n will also be greater than the series B sub n for all n. And we know that this series B sub n is convergent. Okay. If your lesser series is convergent, you do not know any information about your upper series. Okay. We cannot say anything about this. Okay. In comparison, no pun intended, we have part B, A sub n is less than B sub n for all n. So series A sub n is less than series B sub n for all n. Again, we know that series B sub n is convergent. Okay. For your direct comparison test, if your upper series is convergent, you know that your lower series is also convergent. Okay. So series A sub n converges by the comparison test. It's really important, okay? And I also put the second problem in here, number 9, there so that you can see a direct comparison. Again, no pun intended anyway. But basically, it depends on which series you know is convergent or divergent. Let me save that picture. And I'm going to clear out these details. I'm going to keep that 11.4 thing up there for right now. Scroll on down to number 9. Okay, so now we are looking at series A sub n, series B sub n, excuse me, they have positive terms, and we know that series B sub n is divergent. So we're going to compare when A sub n is greater than B sub n with when A sub n is less than B sub n. So for part A, you have A sub n greater than B sub n for all n, which means series A sub n is greater than series B sub n for all n. Okay, and then we know that series B sub n is divergent. Okay, if your lesser series is divergent, then you know your greater series is also divergent by the comparison test. For part B, A sub n less than B sub n for all n. Summation A sub n less than summation B sub n for all n. We know that series B sub n is divergent. Problem is, it's the greater series in this case. So we don't know any information about the lesser series. Okay, we don't know if this is convergent or divergent. Series A sub n, okay? So go over that, double check either with my notes or any videos that you're watching, and then ask me any questions that you might have. All right, I've saved that. Let's move to number 10. Okay, so the next two problems are getting into using our comparison tests For the first one, I'm going to use DCT. For the second one, I'm going to use LCT. I think I'm going to do these ones on a separate whiteboard. Let's go to new share. Okay. All right, so this is exam 3 review. Number 10. Determining series convergence or divergence of S equals summation K from 1 to infinity of ln K divided by K. Now I chose this one because it's actually kind of fun. It's a little bit abstract because you don't get K from 1 to infinity for your regular bounds like you do for some of these other problems. First thing we're going to do, we're going to establish what is A sub n. And A sub n is always the part that's located here inside your summation for S. So that's going to be ln K over K. Realize we can put the parenthesis here, we can drop it. Just note that K is in the argument of ln. Okay, now typically what you want to do when you're looking for B sub n, you want to drop off all the lower powers of things like the terms in the numerator and denominator. Like just a quick example. If I had A sub n equals n to the 4th plus n over n to the 6th, why not? Then my B sub n, I would just want to drop off the n on the top since that's one of the lower powers, keep the max power of the numerator, max power of denominator, and then simplify it. Okay. Now, in this case, it's not as obvious. But essentially, what we're going to do is compare ln K to the function 1. So let's change. So B sub n is prospectively 1 over K. And then what we're going to do is compare A sub n and B sub n. Which one is larger and for which values of n? And I'm doing it again. Be careful here. If you're working with K's, not n's, keep K's, not n's. This is A sub K, B sub K. Compare A sub K and B sub K. So we're comparing ln K over K and 1 over K. Now, both of these are actually positive. They're both greater than 0 for K 1 up to infinity. But for this one, you'd actually need to check. Ln of 1 is actually greater than 1. And ln of 2 is greater than 1. Oh, sorry, my bad. Why'd I say that? There we go. Okay. So let me recheck. So when K is equal to 1, just comparing the top because the bottom is the same, right? So ln of 1 is actually equal to 0. Compare that to 1, it's less than. When K is equal to 2, ln of 2 is still less than 1. It's like 0.69, I believe. And then when K is equal to 3, the tables turn. And that continues for all K values greater than 3. Okay, so what we find here from this information in this chart is that ln k over k will be greater than 1 over k for k between 3 and infinity. Now, I'll probably be pretty sweet on that part. If you still put 1 to infinity, I'll just make a note on it to let you know and not take a point off. But do realize that it will be important in your later math classes to check. Okay, so what we found is that a sub k is larger than b sub k for k values 3 up to infinity. Okay. All right, so then we'll finish this down here. Ln k over k is greater than 1 over k. So we can put a summation in here. Again, if you got this part incorrect, I'll be very lenient about that. Just note that you want to make sure that you're showing the accuracy of this statement. Okay, so now here's the thing. This is where we started, right? S. And if we already had a test for this that we could have used that would have worked, then we wouldn't need to be doing this whole comparison test to even check. What we want to check is summation b sub n in this case. Check series b sub n, because that was our comparison. Okay, so typically whatever you have to compare, that part is going to be easier to compare. Let me repeat that. So whatever you use for your comparison, when you try to analyze the convergence or divergence of that series, it should be easier to analyze than the convergence or divergence of S. Otherwise, you would need to use the test. Okay. So what we find here is that this summation is P series. It's actually the harmonic series with P equaling 1. It's a divergent series. Does this help us in this case? Absolutely. Okay, so definitely state divergent series and state P series, the test you're using for that. And then since we found the lower series to be divergent, that means the upper series must be divergent as well. Okay, so your conclusion is extremely important. Here it goes. Okay, conclusion, since series summation b sub n is divergent by DCT, summation a sub n, which is also a series, also a divergent series. Now, technically, the reason why this works is because series b sub n was less than series a sub n. So you've already showed that part. You don't need to repeat it here. All right, let me save that picture. That covers number 10. That shows you how to use direct comparison test. If you don't put DCT, you just put comparison test, that's fine. Just make sure when you use a limit comparison test, you make sure to state that it's a limit comparison test. Okay, clear all of this. And then number 11, before I hop back. You're determining the series convergence or divergence of S being equal to summation n equals 1 to infinity n plus 1 divided by n to the 5th plus n. And for this one, I decided to give you a multiple choice one to let you know that LCT could be useful here and just to see how you would use it. So we're going to be using LCT. For this part on your formula sheet, you can add this. Okay. The conditions, essentially what we're going to be doing, we're going to be checking L, which is going to be the limit as n goes to infinity of a sub n over b sub n. And a sub n and b sub n are found similarly to what we did for the DCT case. When you find that limit, there's 3 different results you can get. If L is greater than 0, series a sub n converges if and only if, let me move this over. Okay, that didn't work. Come on, man. Okay, there you go. So series a sub n converges if and only if series b sub n converges. So if you can check the convergence of either one of those, you'll know the convergence of the other. Similarly, if series a sub n diverges, okay. Then series b sub n must diverge as well. Okay. So if and only if means that it just goes both ways. So if series a sub n is convergent, then series b sub n is convergent. Or if series b sub n is convergent, series a sub n must be convergent as well, and so on and so forth. So this is the first condition. Second condition is if L is equal to infinity. So if your limit is infinite, series b sub n converges only if series a sub n converges. So you would have to check the convergence of series a sub n before you knew anything about b sub n. Third condition, if L is equal to 0, series a sub n converges if series b sub n converges. So you'd have to check series b sub n first in order to find out anything about series a sub n. Just some added detail for you that you can add because your formula sheet doesn't give that much detail about it. All right, so I'm going to clear all this out now. Okay, So let's put S in orange as always. All right, so here we go. We're going to use the limit comparison test for this. So first thing is to establish what your A sub n and B sub n will be. So A sub n again is what's here inside the summation for S. And B sub n, you're going to want to drop off the lowest powers from the numerator and denominator. So we're going to drop the 1 and the n. And then we can simplify that. That's 1 over n to the 4th. Now find L. And remember, L is the limit as n goes to infinity of A sub n over B sub n. So in this case, that's the limit as n goes to infinity of n plus 1 over n to the 5th plus n. It's divided by 1 over n to the 4th. Remember, you could technically skip that step if you're comfortable with it and just write A sub n multiplied by the reciprocal of B sub n. Now note you have a distribution on the top here because this is technically a factor. So we have n to the 5th plus n to the 4th divided by n to the 5th plus n. We're going to divide top and bottom each term by n to the 5th. And now we have limit n goes to infinity of 1 plus 1 over n divided by 1 plus 1 over n to the 4th. Limit for 1 over n is going to approach 0. Limit for 1 over n to the 4th will approach 0. Limits of the rest will be 1. Okay, so what we found is that L is equal to 1. Okay. I'm going to save that and then erase the top so I have some more room here. Okay. So we found from our exploration that L is equal to 1. By our conclusions, 1 is greater than 0. Okay, which means both series A sub n and series B sub n are convergent or divergent. We don't know yet. Okay, so from here, what you need to do now, you have to test. Either series A sub n or series B sub n. Let's put a reminder up here. A sub n, the sequence was n plus 1 over n to the 5th plus n. And B sub n, the sequence is 1 over n to the 4th. If we're trying to test the series A sub n, that's the same thing as S. So that's not going to help us. Okay. What we want to test, is series B sub n our comparison part. So that's going to be the series in going from 1 to infinity of 1 over into the fourth. That is a P series. P is equal to 4, which is greater than 1, which means series B sub n is indeed convergent. So state your tests and why, and then state your conclusion about each of your series. So since series B sub n is convergent by LCT, series S, which is the same thing as summation A sub n, is also convergent. Okay, so that's our conclusion. That covers number 11. Let's see how much more I want to get through. Okay, let me save that, clear this all out. Stop my share and go back to the notes. Okay, so 12, we're testing our series for convergence or divergence. We're getting into 11.5 now, which is alternating series test. You can find that on the back of your formula sheet. There's a few ways that you could handle this part, but just for simplicity, you only need to state the conditions that are given on the alternating series test on your formula sheet. So essentially, one of the missing conditions on that sheet is that all of your B sub n terms are greater than or equal to 0, so positive terms. But essentially, the conditions I want you to check and actually have written out in your show work. B sub n plus 1 is less than or equal to B sub n for all n within a certain bound you have. It's typically going to be 1 to infinity. And check that the limit as n goes to infinity of your B sub n is equal to 0 for all n over the same boundary. If you have these two conditions, then your initial series, which will have a form like this, is convergent by AST. That would be fine to put for your conclusion. Okay. Now, essentially, where this comes in, when you have negative and positive values showing up in your summation, A sub n will be the part with the negative and positive values, And B sub n is the absolute value of A sub n. So it just gets rid of this negative part here. Okay. So let me hop over to the whiteboard again so I have some space. Okay, so we had test the series for convergence or divergence. 2, 3, U, number 12. And we can call the series S that they gave us S. And the series I was given was 3 over 4 minus 3 over 6 plus 3 over 8 minus 3 over 10 plus 3 over 12 minus so on and so forth. Okay, so from here, what I would suggest, convergent or divergent. So the first thing is to get S in summation form. You can kind of just leave off the negative part for right now. Just kind of think of a pattern between the numbers first. And even before we think about that, let's think about A sub n. We know that the summation typically is n starting at 1 to infinity. And then we're going to have some A sub n here. So for A sub n, think about a pattern between your numbers. On the top, we see that there's always a 3. And on the bottom, you have n equals 1, 2, 3, 4, 5. Find a pattern between these numbers. For our pattern, it's going to be 2n plus 2. And then when you're thinking about the negative part, like what should I be multiplying in terms of a negative number? Well, there we go. Okay, you want to make sure that the negatives fall on the correct n values. So note all the negatives are on even terms for n. We start at n equals 1. We want to have n plus 1. You could also have no, you want n plus 1. Right? And then the best way to check is to actually expand this and make sure it works. We talked about that in 11.1 last week, I believe. Let me know if you need help with it. All right, now B sub n is the absolute value of A sub n. So it's just all the stuff without the negative 1 attached. So 3 over 2n plus 2. Okay, rule of thumb. Whenever you see this part here, the negative stuff, or you see like an alternating values inside your series, then you want to use AST. Okay. So now the first thing, B sub n, no matter what the n value, n being 1 to infinity, it's going to be positive. You don't have to state that part. It's okay. So what we're going to do now, we're going to check the conditions. of AST. First condition was that B sub n plus 1 is less than or equal to B sub n for all n greater than or equal to some value. We'll check that eventually, but for this one, it'll be 1. So the way that you check, you have B sub n here, right? That's 3 over 2n plus 2. You want to check, is that greater than or equal to 3 over 2 times n plus 1 plus 2? So 3 over 2n plus 2 here, right? Plus another 2, it's going to be plus 4. We want to know, is that less than or equal to 3 over 2n plus 2, the quantity, for at least n greater than or equal to 1. And so your way of stating, essentially, it's fine if you just go ahead and put there, but know why this works. 2n plus 4 is greater than 2n plus 2 for n values greater than or equal to 1. So when you have these values in the denominator, your sign will flip. Okay. Okay. And then the second part, we want to check that the limit as n goes to infinity of b sub n is actually equal to 0 for all n within those bounds. So we have the limit as n goes to infinity, b sub n is going to be 3 over 2n plus 2. This denominator will go toward infinity, so the entire thing approaches 0. So the conditions check out to use AST. Okay. Now this is the beautiful part about using AST. Once you check these conditions, you can go ahead and make a statement about your original series, which was series A sub n, the alternating part. Save and clear. Okay. So once you check off those conditions, you're ready for your conclusion. So essentially, since 1 was checked off, 2 was checked off. Series is convergent by AST. Okay, so check off condition 1, check off condition 2, and then make your conclusion. Okay. All right, I think what I'm going to do now, I'm going to go over number 13, and then I'm going to stop this for now. I will carry this back on Thursday, going through numbers 14 through 20, which will cover 11.6 through 11.10. Keep me posted on your progress throughout this entire thing. Let me know if there's anything that you guys need throughout this time. I'll stop share. And then Okay, so number 13 will be our last one. Test for convergence or divergence. We have an alternating series here. We can tell because of the -1 to the n. Okay. I'm going to do this one on the whiteboard as well. So exam 3 review, number 13. Check convergence or divergence of S, which is a summation in from 1 to infinity, -1 to the n, into the fourth, divided by into the fourth, I cannot see that, plus n squared, plus 1. So again, that's your hint that AST will need to be used. So first thing we're going to do, identify your A sub n. That's -1 to the n, into the fourth, over into the fourth, plus n squared plus 1. B sub n is going to be the absolute value of that, into the fourth, over into the fourth, plus n squared plus 1. Let's check our conditions. Okay, so the first condition, Bn plus 1 is less than equal to Bn for n at least from 1 to infinity. And then 2, that the limit n goes to infinity of B sub n is equal to 0 for the same n values. And if both of those check off, we can go ahead and make the statement that S is a convergent series. Okay. Okay. So basically what we're going to do from here, we're going to check the first condition. Oh, that's well, okay, that's what I was pausing for. So this first condition, let me just explain this a little bit. Essentially, it's saying that you want your next term to be less than your previous term. So like you want B sub 1 to be greater than or equal to B sub 2, greater than or equal to B sub 3, and so on and so forth. And technically, you want all those to be greater than or equal to 0. That's the condition you don't have to specifically write in. But kind of think if this is B of n right here, this would be Bn plus 1. Okay, so just saying that our terms are decreasing in size. Okay. So here we have n plus 1 to the 4th divided by n plus 1 to the 4th plus n plus 1 squared plus 1. We want to know if that is less than or equal to n to the 4th, n to the 4th plus n squared plus 1 for n at least within these bounds. So essentially a way of thinking about this, notice that the denominator for this particular term is going to increase a lot faster than any of the other terms here. So this term, and this term will all decrease much let me repeat that. Okay. So this denominator right here will increase much faster than all the rest of the terms. The one that you really care about is this one. Okay. So since you get so much increase from this denominator versus this one, and both these terms are much larger than the numerators, we know that this is confirmed. If you need to do extra confirmation, just plug in some n values to double check. Okay, now, so we found out that's checked off. And then the second condition, we need to check the limit as n goes to infinity of our n to the fourth over n to the fourth plus n squared plus 1. Oh, what happened here? Okay, so we're going to check that limit. Again, you can go ahead and divide top and bottom by n to the fourth each term. So then what we get here is the limit as n goes to infinity of 1 divided by 1 plus 1 over n squared plus 1 over n to the fourth. Approaches 0, approaches 0. So our limit is 1 in this case, which is not equal to 0. So note the second condition does not apply in our case. Okay. All right, so let me go ahead and clear some of this out so I can make my conclusion. Actually, let me leave that part. Okay. So conclusion. Since series, oops, sorry. Since conditions for AST are not met, S summation of A sub n is divergent. And it's actually divergent by the test for divergence from here. Okay. So you can draw that conclusion from the information about B sub n for this particular problem. Okay. Okay, so I'm definitely going to stop there for tonight. It is a lot to do all this at once. I definitely feel for you guys. Pace yourselves. Remember, I'm your advocate during this time. If you need some extra time, you need more time to study, you're just not feeling comfortable, just let me know about any extensions you need and keep me posted on your needs throughout the rest of the semester, okay? All right, so I hope to see you guys on Thursday. And if not, I hope that you at least view this video and you view the next video that I'll be posting on Thursday. All right, have a great night, and I will see you guys soon.